So welcome everybody to our Gamma seminar. Today we have the pleasure to get Adam Maskalaniec, who is going to talk about reductions of super Poisson manifolds. So thank you, Adam, for accepting our invitation. The floor is yours.
Okay, thank you for introduction. At first, I would like to present the outline of my talk. So at first, I'm going to motivate introduction of anti-commuting variables into the framework of differential geometry. Then I will move to the Z2 graded algebras and introduce necessary notions in graded rings and algebras. Then I will present an algebraic approach to smooth manifolds, since it is more convenient to generalize it further to supermanifolds than the usual language of charts and atlases. And then finally, I will move to supermanifolds, and in particular super Poisson manifolds. And then I will present the reduction of super Poisson manifolds in the context of generalized reduction of dynamical systems. So the necessity of introduction of anti-commuting variables to differential geometry comes from quantization of Poisson algebras. Classically, we have a canonical quantization. So assume we think about R to n as a flat smooth manifold with global coordinates q1 up to qn and p1 pn. And then on this manifold, we have a canonical Poisson bracket. So canonical quantization replaces canonical coordinates with self-adjoint operators acting on the Hilbert space of quantum states. And then commutators of those self-adjoint operators correspond to Poisson brackets of these coordinates on R to n. And in quantum mechanics, we would like to introduce to our theory an operator Q that is nilpotent and whose Hermitian adjoint is also nilpotent, and that satisfies also this property. And to have a classical object that corresponds to such quantum object, we need to introduce anti-commuting variables to our differential geometric manifold. Then we see that if those coordinates anti-commute, then they are automatically nilpotent.
Sorry, Adam.
Okay.
Adam?
Yes.
Could you talk a little bit more about the operators Q and Q adjoint? Do you know anything else about them? What do you want from them? Or how to generalize this relation?
How to generalize what? Because I didn't hear you.
If you know anything about the fermionic creation and annihilation operators, what do you want to do with them physically? And if there is some kind of generalization of this construction?
Well, these operators are needed to introduce fermionic fields to quantum field theory. So we want to replace all relations that define bosonic creation and annihilation operators as we define them when we quantize harmonic oscillator. We want to replace all commutators with anti-commutators and create fermionic fields.
Could you, for example, use different fermionic creation and annihilation operators?
Than this one?
Yeah.
Possibly, yes, but I didn't read about this very much, about this quantum mechanical side, because I'm going to present the classical theory.
Yeah, I know that is just.
But I know there are different quantizations. Yes, the canonical is only the name, because it's not canonical in any way.
Okay.
Thinking from the mathematical point of view.
Okay, thank you.
Okay, so a notion that formalizes introduction of those anticommuting variables into differential geometry is a superring or a superalgebra. That is a Z2-graded ring with a unit such that for any two homogeneous elements with degrees respectively denoted by this module of R and module of S, we have such such graded commutation rule. So the basic example we want to consider is the Grassmann algebra of a finite dimensional vector space. That is a K-algebra generated by the unit and by the elements xi1 up to xi(n) that are elements of the canonical basis of our vector space Kn. Then this algebra is freely generated by these elements and then quotient by the following relations that make it graded commutative. It admits a natural decomposition into direct sum of the following form, that that elements of degree 0 are elements that are spanned by the unit, and the product of even number of our generators of Grassmann algebra, and this odd part, the part of degree 1, is spanned by the odd, but by products of odd numbers of those Grassmann generators. So a global version of this Grassmann algebra is in fact the exterior algebra of differential forms on a smooth manifold. Then our operation on this algebra is the wedge product, and it has the superalgebra structure given by the decomposition into the direct sum of two vector subspaces of differential forms of even and odd degree. Once we introduced super rings, we want to define their morphisms to complete definition of category of super rings. So morphisms of super rings are just the usual morphisms of rings that preserve degrees of our elements. So for example, if we have a morphism of supermanifolds, then the induced pullback, viewed as a morphism of two super rings of differential forms, is the morphism of superrings we want because it preserves the degree of the differential forms. So, moreover, we say that a superring is local if it has a unique homogeneous maximal ideal. When we are in the graded category, we want to consider only homogeneous ideals because only quotients by homogeneous ideals preserve the graded structure.
Adam, could you say some more examples about these morphisms?
About these morphisms?
And in the realm of geometry.
In the realm of geometry, well, maybe later when I will introduce supermanifolds that we create out of a graded vector space, then I will say what are morphisms of such object. But now I may say that, for example, if we have any linear automorphism of Kn here, then it naturally induces a morphism of Grassmann algebra that is exactly morphism of superrings. So this is one example. Because then it definitely preserves not only the Z2 degree, but also Z degree. Do you think about any other specific examples or something like that?
There are others. For example, you can think about the hot star operator in the case of manifold that is even dimensional, for example, yeah, it maps even to even, odd to odd, something like that. This is one of the ones you can think of. Or yeah, I was thinking just where this could be done. Yeah. Now I cannot think of more. Well, yes, maybe yes, but they could be a little bit complicated. Okay, but it's enough. Thank you.
The other possible example, I think it would be taking a wedge product with a differential form of even degree. This also.
Yes, that could be. It could be.
Okay. Uh, okay, so let's move on. We would like also to introduce a graded version of Lie algebra. So we want to consider a supervector space, namely a Z2 graded vector space, together with its Lie bracket. And now we want this Lie bracket to be bilinear as usual, but we modify the anti-commutativity of this bracket into the super anti-commutativity, namely anti-commutativity with respect to this sign rule. And similarly, we modify the Jacobi identity. And we may observe that if we reduce this super Lie algebra when we quotient out this odd part, then we obtain a usual Lie algebra. So now to introduce all these algebraic notions to geometry, we would like to change our view on our smooth manifolds, because as I said before, language of charts and atlases is not appropriate to introduce those nilpotent elements. So we know that any smooth manifold can be equivalently described as a locally ringed space that is a pair M and C infinity M, where M is our manifold viewed as a topological space, and C infinity M is a sheaf of smooth functions on M. Namely, it is a functor that assigns to each open set on M a ring of smooth functions on M. And it is a sheaf because this assignment is compatible with restrictions. And now we may say that smooth manifolds are a full subcategory of the category of locally ringed spaces. And smooth manifolds are exactly the locally ringed spaces given by those locally ringed spaces that are locally isomorphic to Rp together with the sheaf of smooth functions on Rp. So these are topological spaces together with functions on those topological spaces that locally look like those smooth functions. Okay. And let me establish one important thing about notation. So if we are given a locally ringed space, then the evaluation morphism is a map that assigns to each function quotient of induced element in the stock at point X by the unique maximal ideal in this stock. And how it looks, how this abstract setting looks in the case of smooth manifolds. So in the case of smooth manifolds, this stock is just a ring of equivalence classes of functions that in a neighborhood of the point X are equal. And then the unique maximal ideal in this stock is the ideal of functions whose value at X is 0. So then, according to its name, the evaluation morphism is exactly taking value at X. But in the more abstract setting, for example, in supergeometry, it is not exactly the same. And to accomplish this presentation of algebraic approach to smooth manifolds, I would like to recall a classical example, namely the Milnor's exercise. So if we are given the evaluation map, then this evaluation map takes value in real numbers. So clearly then its kernel is a maximal ideal, because quotient by this kernel is a field. And then it turns out that all maximal ideals in the ring of smooth functions on manifolds are exactly ideals that are kernels of evaluation morphisms at certain points. So then it is also not very surprising that if if we have such a bijection, then using those smooth functions, we may reconstruct a topology on this set of maximal ideals in the way that it exactly coincides with the topology of M. And if we have such a construction, then again, we may consider real valued functions on such a reconstructed topological space. So given a ring of smooth functions on a manifold, we may reconstruct its topological space. And from this topological space, again, we can construct a ring of smooth functions. So everything here is equivalent, and it turns out that in supergeometry, it is different. So now we may define supermanifolds in this language. So a superringed space is a topological space M together with a sheaf calligraphic O with subscript M. And now our sheaf is a sheaf of superrings. So OM assigns to each open subset in M a superring, but not a usual commutative ring. And all restriction morphisms in this sheaf are morphisms of superrings. Moreover, we define morphisms of superringed spaces in such a way that we want these morphisms to be even on level of each open subset. And we remember that a local model for a smooth manifold was a space Rp together with a ring of smooth functions on Rp. And a local model for smooth supermanifolds will be a topological space Rp together with a sheaf that is a tensor product over R of smooth functions on Rp. I'm sorry, here there is a typo. Here it should be P. Tensored over R with the Grassmann algebra of RQ. So we see that in this local model, elements of the ring C infinity PQ of V, the ring of superfunctions, can be expressed as F0, where F0 is a smooth function, plus Fi times theta I. And from now on, I will denote by I a multi-index, namely an element of Z2 to the power of K. So now there comes the first difference between smooth manifolds and supermanifolds. It turns out that the unique maximal ideal in this stock of locally defined superfunctions is given by equivalence classes of those locally defined superfunctions that their zeroth component with zero component with respect to the decomposition I showed on the previous slide here is equal to 0. So this can be proved purely algebraically, and it is also completely independent on any choice of coordinates. Moreover, I think it's quite intuitive that we lose all the information about the nilpotent part because mx has to be a maximal ideal, so it is also a prime ideal, so then all nilpotents definitely belong to this ideal. So we do not so we lose all the information about nilpotents when we quotient by mx. So as I said, the evaluation loses all the information about the nilpotent part. And as I announced, a smooth supermanifold is a locally ringed space that is locally isomorphic not to Rp, but to a superdomain I introduced. So we have a cover of open subsets of M such that there exist open subsets of Rp. With this calligraphic T, I denote the topology of Rp such that we have compatible isomorphisms of our locally ringed spaces. So let me move to the examples. So if we consider any smooth manifold M, then the sheaf of differential forms endows M with a supermanifold structure. And indeed, if we have a coordinate system on an open subset of M, then we see that the algebra of differential forms is generated by differentials of those local coordinates. So it is exactly the local model we wanted. And moreover, as I announced, if we are given a supervector space, namely a vector space that admits a canonical decomposition into the direct sum, then we may endow this vector space with a structure of a supermanifold. So naturally, we may see that V star can be considered as a subset of the set of smooth functions on V. So then it is natural to define a supermanifold whose topological space is V0 and AV is a sheaf of superfunctions such that AV is equal to the sheaf of smooth functions of V0 tensored with the exterior algebra of V1. Then, if we are given any basis of V star, this basis then gives us a supercoordinate system on V viewed as a supermanifold. And now we may see that if we are given any morphism of supervector spaces between V and W that preserves the degree, it naturally induces a morphism of supermanifolds constructed in this way.
Adam, could you comment briefly on the canonical example of a supermanifold given by the Bachelor-Gavensky theorem?
Yes, of course. So suppose we are given a manifold M and a vector bundle E, whose underlying smooth manifold is exactly M. Then we may consider the exterior power of our vector bundle E. And then, since E is locally trivial, the exterior product of E locally has the desired form of tensor product of smooth functions with the Grassmann algebra. So this is a canonical example of a supermanifold, and the operation of multiplication in this supermanifold is exactly the wedge product in this vector bundle. And it turns out that any supermanifold can be non-canonically identified with such a structure.
That's what I was about to say. Thank you. It's the most important example that in practice one tries to find coordinates in a supermanifold in such a way that it is written in this manner. Yeah, it's very practical and very interesting that the global leader is such an isomorphism between any supermanifold and a supermanifold of this type.
And it turns out that on supermanifolds, we may partially recover the results of Super-Milnor's exercise. Again, we may consider the evaluation map and kernels of evaluation maps at all points of the underlying topological space M. Then we obtain a set of maximal ideals, and there is a bijection between the set M, the underlying topological space M, and the maximal spectrum of the superring of global sections. But then, if we are given this topological space, there is no way we can recover the information about the nilpotent part. So this underlying topological space does not define fully the structure of a supermanifold. Moreover, if we want to recover the topology of M on the set of maximal ideals, the procedure is very similar, but we take this evaluation morphisms, so we lose again all information about the nilpotents in the topology. It is very similar to the algebraic geometry setting when we are given any algebraic variety and its reduced part, then both have the same topology, but algebraically they are different. So as you maybe guessed already, if we are given any superfunction f of this form f0 plus sum of fi times theta I, then we may cancel this part and obtain a function, a smooth function on M. And this is done completely invariantly without using any coordinates using these evaluation morphisms. And we obtain a surjective morphism of algebras from the ring of superfunction into the image of this map epsilon. Then we may proceed with this construction on any open subset and obtain a short exact sequence of sheaves. And then by local triviality of our supermanifolds that locally look like C infinity of M times the Grassmann algebra, this F is locally isomorphic to C infinity of M. So if we are given any supermanifold with a topological space M, then we may endow it canonically with a structure of a smooth manifold that we already recovered. And this construction is completely natural, so it gives rise to a functor from the category of supermanifolds to the category of manifolds. To perform the Poisson reduction and the Poisson supermanifold setting on our supermanifolds, we also need to introduce supervector fields. And again, we turn to the algebraic formulation, and we observe that on smooth manifolds, vector fields correspond exactly to derivations of the ring of smooth functions. So we extend the notion of a derivation in this graded way to a super derivation that satisfies this modified Leibniz rule. It is modified with respect to the degree of this derivation, the degree as a map of super vector spaces, and the degree of A. And we say that a super vector field is a super derivation of the super function. And super vector fields form a locally free sheaf of OM modules on our supermanifolds. And if we are given a global coordinates ti and theta alpha on a supermanifold, then this module is generated by differentiations with respect to those coordinates. And this is a very convenient approach, since there were the other possible formulations of theory of supermanifolds that already are mostly out of use, that used this language of charts and atlases. And then in this setting, there were results where there were super vector fields that weren't section of the sheaf that was locally free. So it was not locally generated by such derivations. So now it is basically out of use. We also extend a graded commutator. We also extend a commutator to the graded commutator by adding again this sign factor here. So maybe I will skip this part and move forward to the example. So if we are given a smooth manifold that is a supermanifold together with the sheaf of differential functions, then the exterior derivative is a supervector field on M. And the graded Lie bracket of D with itself is 0, because D is of degree 1. On supermanifolds, we may again consider distributions. And now distributions are locally free submodules of the sheaf of derivations that admit a complementary submodule D prime. And with respect to this graded commutator, we may define involutivity of those derivations. And it turns out that we may recover the famous Frobenius theorem that a distribution on a supermanifold is involutive if and only if it is integrable. But now we see that this graded commutator had also factors that come from this odd part. So we may have additional obstructions coming from this odd part, the obstructions that forbid us to integrate certain distributions. And the last ingredient of the supermanifold theory I would like to mention is that we obtain superdifferential forms just as a dual of the module of super vector fields. And if we consider super differential forms together with the wedge product, then it turns out that the proper notion of the wedge product also depends on the degree of omega. So we obtain a different sign rule for super differential forms. And the proper notion to describe super differential forms in the language of supermanifolds is to give them the structure not of a supermanifold, that is a Z2 graded manifold, but of a Z2 graded manifold, but I will not mention it. These were objects introduced by my supervisor, Professor Grabowski. And they give natural extensions to the theory of jet bundles and so on. Okay, so finally we moved to this Poisson part. And again, we modify our algebraic structure by replacing the traditional ingredients of our definition of super Poisson algebra with their graded counterparts. So we replace the Poisson bracket with a super Lie bracket and the product with a graded product.
No.
So
paręnaście wyciągał. Teraz może
have some guests here. Okay. So a super Poisson algebra is a super algebra that together with this Lie bracket is a super algebra and satisfies this graded Leibniz rule. So this graded Leibniz rule exactly means that taking the operation of taking a bracket with a super function is a derivation. So if we define Poisson supermanifolds to be supermanifolds whose sections are Poisson algebras, then we immediately observe that to each superfunction we may for each superfunction we may define a super derivation xf that is exactly taking the Poisson bracket with f, and by its definition it is a super vector field on a super manifold. Moreover, by the duality between super vector fields and super differential forms, we may observe that the Poisson bracket of f with g is exactly evaluation of the super vector field at xf on g. And then we see that our Poisson bracket depends only on the exterior derivative of g, but not on g itself. And we may proceed similarly for f. So then we see that we have the super Poisson vector.
Sorry, Adam. Just one remark about what you've written. It's a little bit misleading. Okay, or it can be problematic what you brought, because in supergeometry, each time you change the order of variables, for example, f or g, between the second and the third expressions in the equality, okay, the second equality, yeah, the second and the third members, you notice that you have changed the order from if and g, yeah? Do you see it?
Between f and g,
because you can write, yeah, between
yes,
this
exactly
and
the same.
Yeah, the problem is, the problem is that when you write, the second step is the vector fields, the vector field related to the super function f applied to g. And then you have written dg and xf. So you have changed the order in which appear the function f and g. Normally, the standard notation is that when you change the order of variables in the expression, a factor appears, and this factor is the 1 minus 1 order f or the order g. Yeah, this should be in the second one. Okay, and then you can write, yes, wait a second, it will be, yeah. And then using that, you should be able to go to the following one. Straightforwardly by definition. Definitions are different. Let me as a second, okay? Right, because this is it should be the same, and something here is queer, okay?
Well, it depends on the convention because
Yeah, but
you
your
may
convention
change
is
it,
very,
and I
I
think
mean,
the convention you mentioned is that this is exactly this, but then you have the inner product.
yeah, this is something different. So the normal thing
And
you
this is
wrote, yeah,
different than the inner product,
yeah,
exactly by the same factor.
normally the thing you do is you to write the inner product in the third part of this expression, and everything then goes nicely. Yeah, and something is here weird about that. This is not the usual stuff, okay? Because normally you always in supergeometry, there's a general rule that tells you that whenever two superfunctions change the order and they are homogeneous, some factor minus one of the order of the first function and the second must appear. So this what you have written for sure at the very end it should be okay, yeah, it should be correct, but the way of writing it can be contrary to the standard norm and it can lead to contradictions, okay. This is the only remark, yes, but you know that this is problematic, that if you change that it's always a problem.
Yes, I know, but if I remember well, and now I am already looking at this paper, I took this equation, this convention, this whole convention, from the article of Iborzu.
Well, it may be, but anyhow, it's not the standard.
Okay. So we would like to consider actions of super Lie groups on super manifolds, and there is only one way to properly define a notion of a super Lie group, namely to use the abstract nonsense. We define a super Lie group to be a group object in the category of supermanifolds, namely a supermanifold with operations of multiplication, inverse, and neutral element that are morphisms of supermanifolds and satisfy the following commutative diagrams. And completely analogously, we categorically fix the notion of action of a super Lie group on a supermanifold.
Adam,
Now,
yes, a comment. I liked the. It was fun to say that it is the abstract, the nonsense abstract. Yes, one comment. The thing that these diagrams you saw, they are a way of introducing even common Lie groups. But the problem is at that level, they introduce certain parts that they can be obtained by definition of other parts. I mean, the definition given by these diagrams in the standard case can be simplified. They are redundant things. But as you said, to extend these to super Lie groups is the only manner to do so in a nice way. Thank you.
okay. So now I would like to proceed to the generalized reduction procedure. So at first, let me say what is a generalized reduction of smooth manifold. So we consider a smooth manifold and a vector field on this smooth manifold that models our dynamical system. So reduction of such system consists of two steps. At first, we may choose a submanifold N such that X at any point of this submanifold N is tangent to this submanifold. So the flow of X leaves this submanifold invariant. And then we may proceed with the second step. We may consider any equivalence relation R on the submanifold N that is compatible with the flow. Namely, this condition is satisfied, so this means that this flow leaves our equivalence relation invariant. And if we recall our standard Marsden-Weinstein reduction by means of the momentum map, then it exactly fits in this picture. because at first we take the level set of the momentum map. So this is our submanifold N. And then we quotient by the action of stabilizer of mu under the coadjoint action. So our Marsden-Weinstein reduction is an example of such a procedure. Then this procedure has a dual version. So at first, we may consider a commutative algebra A and a derivation of this algebra. Then those two steps are the following. At first, we may choose an ideal that is preserved by this derivation. So then this derivation x induces a derivation xb on the quotient. And then we may consider a subalgebra of this quotient that is preserved under this induced derivation xb. So why is it the same? So at first, we have the following theorem that there is a bijection between closed embedded submanifolds of M, both in case of smooth manifolds and supermanifolds, and the set of regular ideals. The regular ideals are the ideals that satisfy certain properties that make this quotient just isomorphic to the smooth manifold M. And these ideals are constructed in the following way, that if we are given a submanifold N in the manifold M, then we consider the ideal of functions that are vanishing on M. And this is the corresponding ideals. And for the second step, if we are given a submersion of supermanifolds, but this also works in the case of smooth manifolds, then by the definition, each induced tangent map is surjective. So the induced map of global sections is injective. So we obtain the subalgebra of sections of M. So this is just the algebraic picture of the previous version of our reduction. And then I would like to perform the reduction of super Poisson manifold exactly following this generalized approach. So at first, I consider a closed embedding of a supermanifold M into super Poisson manifold P, and this embedding corresponds to the sheaf of ideals I. Then we may assume that we are given a subbundle of derivations of P restricted to M, namely a submodule of derivations of P restricted to M. And then I would like to formulate three conditions that make our assumptions equivalent to the picture I showed you before here. So at first, we assume that E intersected with OM is an integrable distribution in OM. And exactly here, we need this algebraic approach to define this intersection. Because intersection of E with derivations of OM are exactly those derivations of OP that preserve this vanishing ideal of our supermanifold M. So just to define the intersection, we really need to take this algebraic point of view. And next, if this is an integrable distribution, we want to assume that this distribution induces a foliation. And then this foliation corresponds to the subalgebra invariant to the subalgebra of superfunctions that vanish under the action of our derivations. And we also need the next condition. The bundle E leaves the super Poisson bracket invariant. So leaving this super Poisson bracket invariant means that the supervector fields of the form F induced by this Poisson bracket will be left invariant by our operations. So these are conditions for compatibility of our submanifold and our quotient structures with flows of supervector fields of this form. And we say that our triple is Poisson reducible if we have a unique induced structure of a super Poisson manifold on the quotient of our submanifold M by our foliation F. So now we may generalize this Poisson reduction theorem by Ibord, saying that the triple PME is Poisson reducible if this super Poisson bivector induced by our Poisson structure has the property that it maps annihilator of E into the derivations of M plus E. And now let me once more lower the level of abstraction. And now we want to consider the fundamental vector fields induced by the action A. The action A is fully defined algebraically by the pullback of superfunctions. So we compose it with the tangent vectors to the super Lie group at the identity element, and we obtain fundamental vector fields in this algebraic way. Then we say that this action is a Poisson action if those fundamental vector fields are generated by certain superfunctions. And the assignment of those superfunctions to the elements of the tangent space to the super Lie group, our super Lie algebra, defines the so-called comomentum map. And this comomentum map gives rise to a morphism of supermanifolds. This constitutes a morphism from the super Poisson manifold P to the super Poisson manifold that corresponds to the dual of the super Lie algebra. And then we obtain a very similar formulation to the classical Marsden-Weinstein reduction. So suppose we are given an action A on the super Poisson manifold P together with a supermomentum map J. If we are given a regular value of this supermomentum map and the stabilizer subgroup of the element M with respect to the coadjoint action acts on the fiber of this morphism freely and properly, then the quotient supermanifold is a super Poisson manifold, and this has those nice properties written down here. I would like to remark that properness of our action is purely topological property. So it is the same in the case of supermanifolds and reduced smooth manifolds. But freeness also gives us some conditions on those elements of degree 1. And this classical theorem can be exactly proved just by application of our previous generalized super Poisson reduction. So we take our submanifold M of the super Poisson manifold P to be the fiber of the supermomentum map, and we take our distribution E to be a distribution spanned by the fundamental supervector fields. Then the intersection of E with derivations of M is spanned by the fundamental vector fields that correspond two elements of the stabilizer of the superalgebra of the stabilizer subgroup G mu. As G mu acts freely and properly, this intersection is an integrable distribution, and the super Jacobi identity gives us compatibility of this construction with the Poisson bracket. Moreover, we may verify the final condition given in this generalized super Poisson reduction theorem, namely that this super Poisson bivector maps our annihilator into the derivations of our submanifold J inverse of mu. And this is proved by means of the super-Poincare lemma, because it turns out that locally also super-differential forms are exterior derivatives of superfunctions. Then we see that if we are given alpha u in the annihilator of E, then this is alpha u, then 0 is equal to alpha u evaluated on this fundamental vector field, but then, since alpha u is equal to df, this is evaluation of this fundamental vector field on the primitive form of alpha, namely the superfunction f. On the other hand, the super Poisson bivector acting on alpha u gives us this Poisson bracket with f. And then we directly calculate that dA psi acting on f is 0, so our condition is satisfied. So it turns out that many very well-known procedures of reduction exactly fit into this algebraic picture. And in further work, I plan to analyze it in the setting of reduction with singularities, because this purely algebraic picture is a very good framework for further generalizations. So at the end of my talk, I would like to show you the articles that are very useful in learning of this topic. At first, I would like to advise you to see this article on generalized reduction procedure, because it not only can be applied to the supermanifold case, but also to other settings, also algebraic geometry settings and non-commutative geometry in the sense of Alan Kohn. I also heavily relied on the article of Gerald Marsden on the generalized reduction, but only in case of smooth manifolds. And there is a great book of Carmeli Caston-Fioresi on supermanifold. That is a very modern textbook. So thank you for your attention, and please ask me some questions.
So thank you, Adam, for your talk. It's been very clear. So is there any question, remark? Okay, for me, I could make a remark, but Adam knows pretty well that we have to look for particular examples of all this stuff, yeah, because it's always theoretical, and no many people applies this to particular cases, a particular example. So it's something to do. The other thing is that, could you comment on the paper by Grabowski, Land, and Marmon Bilasi about the generalized reduction procedure? Could you talk a little bit about what is done there?
What is done is the proof that those two pictures, this algebraic one and this manifold setting, are equivalent. So this paper basically proves equivalence between this slide and the next one, the algebraic structure. And since one of the co-authors is Professor Giovanni Landi, who is specialized in non-commutative geometry, then it is applied to examples of reductions in non-commutative geometry. So a big part of this paper also involves non-commutative geometry, but it doesn't say anything about the algebraic geometry or supergeometry. But it is very general and very powerful. So what is left to be done in the other possibilities is to verify how our algebraic structures define geometric objects and how those quotients induce certain types of geometric structures. So we need to investigate all those regularity conditions that make our quotients algebraic objects that correspond to certain smooth manifolds or orbifolds or anything else.
Okay, thank you. Is there any question, remark? No, so thank you, Adam. It's been a good, nice talk. Thank you.
Okay,
so,
thank you.
Xavi, you can finish the recording. I will write to Xavi. Or I will try to switch it off. Right? Maybe I can. Captions.
Possibly Xavi is now collecting works of his students. So
No,
might be busy.
I think that it should be an hour, not